Believe? Okay, let's go. So this is COMSOL. It is open. You come into blank model and click blank model. Why is my mouse blinking?
It's recording.
Yeah, but I don't think the idea was for my mouse to be blinking.
It's never happened to me before.
Okay. So hide that notification. Okay, so the first thing that we're going to do is we're going to create some geometry. So we're going to click here, Component, 3D. Okay. And now that we have this 3D component, we can right-click on Geometry and say Import. Okay. Then this you click Import, and this little screen will open here. This is when you have to select a file to import. So we will say, we'll click Browse, and we're going to go and select a file to import. So that can be, we go to the research drive, and we select another 3D model. So simulations, piezoelectric resonant motor, COMSOL conference, SEM. Let's go here. 3D model, single mode patterning. I guess we can use this one. So I'll copy this one outside here so we can create a new, let's call it a Piezo tutorial. Motor tutorial. Okay. And we're going to paste the model here. Okay. Then we will go and we're going to choose this model. So the assembly is this one, correct? But there are two. There is this assembly 1 V2. I'm assuming it's a V2. So we will click here and say open. And then length of units, COMSOL. If we're going to use the one from COMSOL, we should set it up. So let's quickly set up the units. We click here in, where do we set up the, we click here in geometry and set millimeters as the unit. So we go back to the import. From COMSOL, solids, everything else looks nice, and we click import. And this imports the SolidWorks model. So it's importing the SolidWorks model into COMSOL.
Okay. But what do you pass? This is a function, right?
Yes.
Okay. Ta-da. We have the model in here. Okay, model, we can rotate it around, everything is good, the model up here is correct. So now, we want to remove these lines. See these little lines here? Like that line there. This red line. Those lines cause problems when we mesh. So we will click here, Geometry. We're going to say Virtual Operations, Ignore Edges. And we're going to select all of these lines that cause problems, which is this one, this one, these two,
right, so on the second iteration of loop, what do you pass it?
this one,
number. It's whatever the time step is for the planet on.
this one,
Time is first given.
that one,
Time is first passed in.
this one, that one,
So time is passed into the 45.
And you get back out of this time.
this one,
You get back out of the time back there.
that one,
So T. So if I'm passing
this
T
one,
with planet ROV, I'm also passing T within that to the place.
Oh, I see what you're doing.
So it's synchronized.
Okay. Got it.
okay? So I think we have selected all the lines that have to be removed. Actually, are these selected? Selected, selected, selected. Okay, so all the lines that had to be selected seem to be selected except for these two here. This one, that one. This here, that there. Okay, we have selected all the lines. Good. So now we click Build All, and these lines disappear. Good? So now we have the geometry imported here. So we can move on to the next step, which is, wait, let's make sure that all the lines are gone. Yep, all the lines are gone. Okay, so now the next step is to import physics. So we're going to go to physics, say add multiphysics. Before adding, let's add normal physics first. So add physics, and we're going to come here and select. We need solid mechanics. We need piezoelectric. Let's just add a piezoelectric because that one adds all of them. So let's see where it could be. Structural mechanics, piezoelectric devices. Okay, add to component. And that should import electrostatics, solid mechanics, and a piezoelectric coupling.
So that's probably why.
That's could be called.
Okay, so now we have here solid mechanics, electrostatics, and the coupling. So there are a few things to do here. Let's also add the materials. So we're going to add first a blank material.
It's like, well, you're not giving me
That will be the copper. Okay. So this blank material, let's call it copper, or actually stator material, whatever it is. Let's just be more generic, because you might want to use this one here that you did. Another blank material that we need is the epoxy. Okay. And we need the actual piezoelectric material, which we can just add from the library. So we can go here to Recent Materials and add PZT 5H. So let's type here PZT and search. So we're searching now for PZT.
Yes, they can.
If it goes over 10,
Yeah.
then
PZT 5H. See? PZT 5H.
What's the difference
Yeah, the
between
components.
those?
They have different material properties. They're completely different materials. 5H just happens to be the one that we have here.
Like somewhere in that range.
Okay? All the material properties are here.
Because the way
Now,
like, ODT
for the
works
stator.
is it increments T by like tiny bits.
We need, so these properties are actually incorrect. So before we do this, we might have to set the correct properties to appear. And
that's how it works.
let's just see this. Okay, so let's apply first the materials to where they have to be. So the stator is supposed to be only on the stator. So we can delete from all and select just this. So that's the stator material.
And they're like,
This is the epoxy material. So let's select only the epoxy.
it's not
And
the other
this is for the piezoelectric material, which are these parts here on the bottom. Okay, so you click on all the ones you want, and now they're selected.
in my
Okay. Now the epoxy, another thing. So see that it's requiring this relative permittivity and these things which are electrical properties. So that it doesn't do this, you have to come to electrostatics and deselect everything that should have no electrostatics. There is no electrostatics in the stator or in this. Okay. So now if we go back to the material, it apparently didn't update, but it will in the future. Same thing here with piezoelectric effect. The piezoelectric effect is just there. Yep. Okay, so that's correct now. And solid mechanics is everywhere. So now let's go to the stator. You are telling me that the density of this mystical material that you found is
2,520. 2520. Yeah.
2520. This doesn't matter, this doesn't matter, this doesn't matter. But we need some other materials properties. We need Young's modulus and Poisson's ratio. So let's add here Poisson's ratio and Young's modulus. So the Poisson's ratio is 0.29.
9.
And the Young's modulus is
66 G.
66 E9 gigapascals. Okay? The epoxy, we can copy from another simulation we have. So let's open here the other simulation, which is already open. Baseline plastic. Let's take a look what the epoxy properties are. So material here, epoxy. It's 3500, 0.43, and 0.7. Okay? So 3500, we add the other materials. Poisson's ratio, which is just 0.33, and Young's modulus, which is 0.7 E9. Okay, so now all the materials are defined. Okay? Now let's move on to solid mechanics.
Are you gonna?
And let's make sure that everything is set up properly here.
Yeah.
You will?
Yeah, I'll,
Okay, no, I'm just gonna
Alright.
make the reservation. I got you now.
Cool.
let's see, there's something here behaving a little bit weird. So solid mechanics, okay, is everywhere. But for some reason, it's not accepting this as a linear elastic material. So let's understand why. Because piezoelectric material is selected. And the only piezoelectric material is supposed to be the bottom one here. Okay?
I'll try to buy the stuff tomorrow.
So now if we go to solid to elastic, linear elastic, these two materials on top are linear elastic materials because they're no longer piezoelectric, so it becomes the other one. Which means that now in the materials, see the other weird properties disappeared. And it accepted the ones we gave them.
Yeah.
You have to right-click solid mechanics and add a fixed constraint because something in the simulation has to be fixed. And what will be fixed will be this top and bottom surface because that's what is being pressed by the nut. So the top and bottom are fixed to the universe.
This is the boundary condition.
This is the boundary condition.
Okay.
Yes. So now electrostatics. We need to excite something. So before we excite something, we need to ground something. Okay, so we can come here and add a ground. And the ground will be the top of all the piezoelectric elements. The way we're going to do that is that we're going to hide some things from sight. So we're going to click here in this volume thing, click hide, view only unhidden, and we're going to hide some of these materials. Okay, so we're going to hide this, which for some reason it's not letting me hide it. Let's click this again, click there. Why is it doing this? Okay, so we're going to hide that. That should be enough for us to click. Then we are going to deselect this hiding thing, click ground, click this little box, and we're going to select the top of each one of these elements. Okay, the top of each one. The top of each one will be selected. Okay, now the top of everything is ground. And we're going to reset the hiding. And everything seems correct, everything is blue on top. Okay, and the next thing that we need is that we need to actually excite the material. So we click electrostatics, and we need 4 phases of excitation. So we're going to create basically 4 electric potentials. The electric potentials, so we're going to define a variable that will be the voltage. We come here to parameters, and we can call this V0, or I don't know, it can be VI. I don't know. VI is a good enough number. Which will have a value of, let's say, 100 volts. In square parentheses indicate units, so 100 volts, like that. So now when we come here, we can say that this will be VI times sine of, we need to have a frequency, okay? We can call freq 0 if we're in the time domain. We need to define that here, so we'll define that freq 0 to be, let's say, for now, 50 kilohertz. Lowercase k. Oh, so it doesn't work. It's very specific. So this will be freq 0 times 2 times pi, because this is in radians, times t, which will be time. So is this correct? So it's the frequency times 2 times pi times t divided by 180 plus some phase, which we can call phase 0. Actually, don't need for the phase to be like that. The phase will just be pi, will be 0 in this case, because this is just a sine wave. So let's confirm that this equation is correct, looking at the other model, so we don't have a silly mistake. So if we go here, 180, so that's a voltage, and then call VI, 2 times pi times freq 0 times t plus 0. So in this case, it did not divide by 180. Should I have?
What is that? You have a 180 at the outside of the side.
No, this 180 is something else. It's just a voltage. So this so let's not divide by 180 inside, correct? Or do we have to divide by 180 inside?
No, pi is the radian. Pi stands for 3
And frequency is equal to 2 pi. Actually, omega is equal to 2 pi f, correct? So if we want omega, it's just 2 pi f. There is no
Yes.
180. Yeah.
No 180.
Okay.
It's the degree you need to divide it by 180. Then you can get a radian.
Yes.
So you have the pi now, so no 180.
So here we can just remove the 180. Okay? We will call this electrical potential the positive sign. So let's call this plus sign. We also need, so why is it throwing a little error? What is this warning about? Oh, it's not applied anywhere, so that doesn't matter. So we will duplicate this. This here will be the minus sign now. Okay? And we will rename it appropriately to be minus sign. Then we're going to duplicate both of these. And now we're going to have the positive cosine and the negative cosine. Okay? And here, to make it cosine, just shift by pi over 2. Ta-da. Good? So now we have all the equations. Now let's apply these equations to the correct element. So if we look at the bottom,
Wait. It's a minus at the top, so it's just a plus pi over 2 or minus.
cosine is a sine wave shifted by plus pi over 2.
Okay.
So if we have
Same
here,
actually.
so the positive sign, okay, which is this equation here, this here is a sensing element. So this element here is a sensing element in the middle. It doesn't do anything. So we will choose one side arbitrarily to be sine and the other side to be cosine. So sine and cosine. And we're going to apply positive sign to these two and negative sign to these two. Same thing on the other side. Positive cosine and negative cosine. So if we check, plus sine, minus sine, positive cosine, minus cosine. All the other unconnected elements are sensing elements. They don't have any role in actually actuating the crystal, which is something that we can try to improve in the future. This patterning is in no way the only pattern that exists. We can definitely come up with better patterns. Okay?
Why is the sine cosine?
Hmm.
The sine is here and here. Why minus cosine be here and here? Why not can be here and here?
It can. If you switch that, I think that the only thing it does is it might change the direction of rotation.
Oh, okay.
Yeah, I don't think it actually causes any problems per se.
So
It probably changes something. I'm not entirely sure what it changes, but I think the motor works either way. We should test that. But I have done it both ways.
the pattern you are designing here, you say is one of the pattern.
Yeah, as in, there is no reason why we have to use this pattern. This is just a common pattern. Yeah, we can definitely try to come up with better patterns that make use of more of the crystals. For example, we have not been using the sensing elements. Some companies use these elements to sense. We are not doing that, so we could just use them to actuate. And that way we have more crystal actuating, the motor will be stronger.
Okay.
So all these things are things we can consider.
So every element should be the same. It cannot be like one is larger,
This
Right.
one is smaller. All of these four are the same size.
that
These
the-
four, these are smaller.
Citation unit should be the same area. Each one.
No, they can be all
No-
different
no
sizes,
eight.
but there has to be a point in having them different sizes. They cannot be, as in, if you're going to make them different sizes, there has to be some rationale behind it. I'm not entirely sure what it would be the benefit. There might be. And there's some very specific circumstances. So we have everything that we need here now, correct? We can excite the crystals. The crystals are grounded. The only thing that uses electrostatics is this bottom part. The piezoelectric materials are clearly defined. We have fixed the inner side of the stator. We have the materials defined. We have imported our geometry. And now we need to mesh. So we can click here on mesh.
Okay, I'll let you know.
And the easiest way to mesh is just keep the standard mesh and say, which is a free tetrahedral. So we can just give it a size. Oh, let me delete this. For some reason, it duplicated that.
Um,
So by default, it will just default to a free tetrahedron. Let's be more explicit, just because.
it's the right
Okay, let's just come here and say maybe free
X
tetrahedron.
is like maybe a-
Do we like that, or no? It's okay. Let's just try to do size and see if it defaults correctly.
So
Just do a normal mesh, just so it's faster. Okay, so yeah, so the problem that I thought would happen happened. We have to just add free tetrahedron and be specific as to the type of meshing that we want. So we're going to do a free tetrahedron mesh.
X.
Okay? And we're going to do something pretty straightforward, just like normal. Build O. And it's building the mesh.
I'm pretty sure it's the output of like solver.
Just a normal mesh. There's nothing, it's not necessarily optimized in any way. There's nothing special about it. Just something that runs fast for us to see. Okay, so now we have the mesh. Now we have to add the actual study. So what are we trying to do? Usually, you always start with an eigenfrequency analysis. So let's add the eigenfrequency study first. So we have here the eigenfrequency. Let's switch to kilohertz because it's easier to think about things in kilohertz. We're going to search for frequencies around 40 kilohertz because we know from experience that a crystal tends to work around that frequency. If you change size or anything else, you have to change this also. And let's look for 40 different eigenmodes. Arbitrary also, there's no reason. You could or could not include geometric nonlinearity. Works both ways. You don't need to include electrostatics or piezoelectric effect when you're doing an eigenfrequency analysis. Eigenfrequency is a property of the shape and material itself. So it's a structural property. It's not related to electrostatics. There is no excitation when you're doing this this thing. So once you're done with that, you can just click compute. Before we do that, let's save. Since we've been doing this all this time, let's not lose what we're doing.
Tutorial.
Yeah, let's go. Yeah, exactly. Tutorial. What is the name of this material?
Marcor, MACOR.
C-O-R. Okay, so let's save. So it's saving, it has been saved. And we just come here and we say compute. Eigenfrequencies tend to be very fast. They are not something that takes too long to do. So let's see, it's running.
Is this computing the same as the other FEA software?
What?
Like Abacus and ANSYS, they are like pre-compute at the first time, and then check there's no problem, and then it will. If it will incur some problem, it will just
No, this if you click compute, it computes for real.
Okay.
If there is a problem, it will just fail.
Plug in.
And then do it again.
Yeah. Like for example, this the simulation that I'm doing here on the left, it didn't converge all the way. It only converged up to here, which is 70% of the way. For instance. Let's see if there's anything talking us about the progress. It should already have been finished. I don't know why it's taking so long. Maybe it'll take 2 minutes or so.
This is the geometry we have known, which we like reverse engineering on the
Yes.
commercialized product.
Yes.
You are talking about if we change the material, we need to change the size.
Yeah, or
Yes,
anything
Stator.
here. Even changing these little fillets affects the resonance frequency a lot.
So how do we confirm the based on the Young's modulus and the Poisson ratio, and then we reverse back to its redesign its shape.
Okay, so I
Let's do this
finished.
first.
I guess it's more of a trial and error, I think.
Try.
Yeah. Okay, so we can see here the different modes now. See if I click here next, we can see the different ones that appeared. Not seeing the ones that we actually see. For example, this one is one of the ones we like. So this is 1, 2, 3, 4, 5. This is the fifth mode at 63 kilohertz. It's very high. Ideally, this should be at a lower frequency. So the reason it is so high might have to do with the material properties. Maybe the density of this material is particularly low. But this is for this weird geometry. This is not necessarily geometry we need to stick with. Okay, now I've noticed that this is taking a very long time to compute, so let's make the mesh coarser. Well, of course, this is horrible, as the results that this will give us will probably be wrong. But we want to do this just to see results. Okay, so this is coarser. could even go with extra cores just to compute fast, because the time domain simulation, which we have to run next, tends to take a long time to compute. Okay, let's rerun the eigenfrequency. Wait, it threw an error. If there is warnings, we can't continue. Okay, so we'll have to go with coarser. Okay, so this one computed, no errors. So we'll do the eigenfrequency again. It should run much faster now. Let's see.
So for example, this material is different from copper, which based on the copper shape.
Yeah.
This one. So we need to change
The shape
The
to
shape.
work for this material.
how. It's just from the experiment.
Yeah, trial and error in the simulation.
Maybe like the.
As in, I noticed some trends. As in, I know that if you
Yeah.
increase thickness, this happens. If you increase this direction, something else happens. If you change the fillet, something else happens. So once you do enough simulations, you gain an intuition, and then. But there is no analytical means that I can think of to actually figure out what you should change, especially because this is a weird geometry. Even changing this inner shape here affects the simulation. Everything here affects the simulation. Okay, so now we're going to add another study. We're going to compute a study, and we're going to say add study, and you're going to do a time dependent study. We're going to click here, add study. Okay, the study is added now. This here. We're going to go to milliseconds. We can do from 0 to. So we need to choose a frequency. So from the eigenfrequency simulation, seems that 63.864 kilohertz is the frequency where this interesting mode happens. Since we want a time domain at this interesting mode, we will switch this frequency here to be that. So 63.864 kilohertz. Okay. Now we're going to come here to time domain. And this here, the time increment should be small enough such that you have multiple time steps within a single waveform, so that you can see the motion of this data. Or else you're just going to see a bunch of weird timestamps. So what we can do here is that a time can be 1 divided by the freq 0. So this would mean there would be 1 time step per cycle. And we can choose how many time steps we want. Let's say 100. So there'll be 100 time steps in a single cycle of excitation. So that should give us enough information. And this can be something like 2 milliseconds. Okay. And let's show the results while solving. Oh, that can be default. Anything else that we need? Don't think so. Wait, there's an error here. What is the error? Maximum number of range elements exceeded. Oh, because this is in milliseconds, so it's 1,000. Okay. So it will be 1,000 times less than we had before, divided by freq 0, divided by 100. And we can put an orthogonal view and compute. So this should take maybe a few minutes. Not entirely sure, it might be fast, because this is a very coarse mesh. And hopefully it will show us. So there's a convergence plot appearing here. I'll actually stop this just because since they didn't have a stress plot before. Oh, but it still doesn't have one now. Because I was hoping that I could actually show us what it looks like while it's computing, but we can't until we actually compute one until the end. That's unfortunate. Yeah, let's just do it. Okay, so let's go back to computing. It shouldn't take too long to compute because this is a very...
So what is your trend experience? Like increase the thickness of the height, and then what happened?
I will look at what I wrote down and tell you. It has been a very long time since I actually did these simulations. Probably, I don't know, 2 years or something like that.
What's wrong with your eyes?
I don't know. Why?
Oh, he's always had that.
Yeah.
Oh, okay.
It's something exploded and it hit me.
Chemical?
No, like one of those little circular saw things from a Dremel or something like that.
Like the saw didn't hit you, like some component from.
Yeah, like it exploded and a little piece hit me.
Because at first when you're describing it, I was like, no.
Okay, so now it's computing. It's 7% of the way. It's doing its thing here.
So try. You need to try different shape.
Yeah, for example, the number of teeth, everything affects it.
And also the mesh.
The mesh, we should just set a certain mesh to be fixed and never change it. Because as long as the mesh is fine enough, it will not affect the results. It won't affect the results in a significant way.
Okay.
And another thing also that is important that is that we can run parametric sweeps. So if we figure out how to parametrize that geometry, which a possibility would be to just make that entire geometry in COMSOL instead of SolidWorks. So if instead of importing the CAD model, we just make it all in here, we would be able to run a parametric sweep that automatically runs through all different thicknesses and things like that, and just gives us the results and the charts of how everything affects it.
I think it's possible, but drawing something in here, it's
much harder.
It's how to say code base.
No, this is graphical. Also,
Is it
you
graphical?
can. Yeah, I'm pretty sure there might be a way to do it code based, but it's graphical. Yes. But it's not like SolidWorks that you can, for example, tell something to make to something or tell something to go somewhere. You just have to enter all the numbers.
Yes.
So it is.
It's kind
Yeah.
of another type, code base.
Yeah. Basically, yeah.
Everything's like very like segmented.
Just monitoring that it's not filling up the hard drives, because some of these simulations take up a lot of hard drive space. Because it saves all values for the entire mesh, for the values of the simulation, for the entire mesh, for every time step. And here, if we calculate the number of time steps that we have 1,000 divided by 63,000 divided by 100. So this is 1.5 e to the minus 4, and we have 2 divided by 1, 2, 3, 1, 2, 3, 0.5. So we're going to have 13,000 time steps in this simulation that we're running now. So it's going to save all the results for the entire mesh 13,000 times, which takes up sometimes a lot of disk space. So it's good to always monitor to make sure. I actually have a hard drive that is dedicated just to these simulations, which is this workspace too.
Well, when like grading like they have like projects.
So how did it came out the Autumn 1000 shape? Just a try.
Mm-hmm.
So actually we need to kind of find the shape that match the frequency, working frequency of the copper shape.
Not really. It just has to be a frequency that we can excite well. For example, those drivers that I made, they can only really excite up to 60 kilohertz.
So this one can work.
Yeah, so we need something smaller, because if we go above 60 kilohertz, the voltage that the driver can output is lower. Because the piezo motor can be imagined as a capacitor. So the higher the frequency of excitation, the higher the current required to drive it. And those drivers have a certain current limit. So if you keep going up in current, you have to reduce the voltage to reduce the current, because the capacitor current equation depends on voltage and frequency.
I just started using them. And I like them a lot.
And what we want is mode 5 and mode 6.
Yes, those are the two that we care about.
Do it separate things. Class names start in capital. And then you use camel case for that. Camel case.
Yeah.
So like inverse dynamics, right? Do that. That's not gonna matter. Like that's kind of functions I do underscore. This function called the dynamics, right? It wraps around and
Okay, so you wanted each of the function which I'm calling to have accepted function.
yeah. So I had seen it as for kinematics.
So like what happened was when we what I did, I thought of writing in modular so I was good at least one thing. Everything was separate, like one function, and then
I think we can pause now.
The recording.
it's a lot of
I think we can pause.
Okay, so this is the results of simulation. You can see here under results, under stress, you have the what it looks here, and you can iterate through the time steps. Okay, so when we click a different time, this is what it looks like. We definitely didn't simulate for long enough for it to reach steady state. This was only 2 milliseconds. I think it reaches steady state around 3 milliseconds. Usually, in this material, I'm not entirely sure. And we can export the actual results. So we can right-click export, say animation, file. It creates this. And we can come here and say movie type. Select the type, let's say an AVI or WebM, whatever one we think is more appropriate. Browse the correct location. Let's call this export. Put it in this folder. And then name it first export, I don't know, 0 to 2 milliseconds. And 100 frame per frequency. Click there to save. We have to quality, frames per second. So let's check how many frames we have. I usually just click here in all and just say, wait, frame select. Oh, so aspect ratio, usually like 1280. I lock there first and then 1280. With non-Niagara frequency, we actually want stress, which is the time domain one. Stored solutions, time, and we can say manual. So there are 12,000 frames, which is a lot of frames. So let's export just the final frames. So let's export frame, let's say 10,000 in 1 frame increments to 12,000. That would be how many frames? So 2,000 divided by 10 frames per second, 200 seconds. Should be okay, correct? Let's go with 11,000 to 12,000. Oh, in 1 frame increments to 12,773. So we'll export 1,773 frames. 10 frames per second, quality 1. Everything else seems to be correct. And you want to synchronize scales between frames, or else it's weird. Actually, I don't think we even need this many frames. Let's just go from 12,000 to that one there. Let's also save this. Saving might take a little bit of time. Let's save it anyways. Since I'm using the network drive, it's a little bit slow to save. Can take a look here to see.
So for now, we have known that the frequency is too high for this. So how to change? What is the idea of changing its shape? For example, make it thicker.
I don't know. It's completely random.
I mean, actually, I was asking you your trend.
I don't know yet. I have to check. If I wrote it down, and that train only applies to the very specific geometry that I had created, which is the one with no teeth. It will be different from this. And now that you'll have this notch here in the middle also, that might change also. We have to just experiment and see, or create a parameterized simulation in here, which I think is the best approach. And then I'm not entirely sure how you report the results, because you'll have to find the peaks. And it's a little bit tricky. Yeah, I should probably not have saved. The saving is taking longer than I had expected, because this is probably a lot of data.
Let's pause. pause for a while?
Sure, I guess we can pause. Okay, so now that we finished saving, we can actually export it, which means everything is already configured here. We can just click export. And then we wait again.